Chapter M, the natural exponential. So we're interested here in taking the derivative of e to the x. In other words, we're going to look at e to the x. But I'd like to take some time to talk about e and why this is special, because we're used to in algebra seeing things like 3 squared, where 3 is your base and 2 is your exponent. So here we have the base of e, and the exponent is x, which can vary, so this is a function. This will be the function that we'll be interested in working with. But why is this base e so special? See, what makes e stand out? And to understand this, we are going to look at economics. Let's say we put $1 in the bank and we get an unheard of 100% interest after 1 year. Now, this is not going to happen, but for sake of the discussion, it's useful to consider 100% interest rate. So after 1 year, I would have 1 plus 1, and that would be equal to $2. I would get my principal back, what I put in, and then I would get my interest. But now suppose I get my 100% interest applied after 6 months at 50% interest, and then another 6 months at 50% interest. So in other words, I get 1 and a half of it back in 6 months. And then in the second 6 months, I get this principal, which is now a little bit bigger, plus a half. So I'm getting interest on interest. You can think of this first one as 1 plus 1 to the first power. And then you can think of the second one as 1 plus a half to the second power, like that. So if we look at this, this would be 1.5, so that's 3 halves. And we're going to square that, and that's going to be 9 over 4. And 9 fourths, well, 8 fourths would be $2, and a fourth left over would be 0.25. So that's what we would have. We'd have $2.25. In this case, we simply have $2. Get $2 back. Now suppose we have a third given to us every a third of a year, so every 4 months. So then we would have 1 plus a third after the 4 months, and the next 4 months we would have 1 plus a third of what we had at the beginning of that second period, and then there's one more interval of 4 months to make the year. So we have 1 plus a third, and we can look at this as 1 plus a third cubed. You can see a pattern here: 1 plus 1 to the first power, 1 plus a half squared, 1 plus a third cubed. This will help us. We'll do one more here. So this is going to be 4 thirds. 1 and a third is 4 thirds. So 4 thirds. And since we're cubing that, 4 times 4 is 16. And we're going to do it one more time. 3 times 3 is 9. And we'll do it one more time. So 16 times 4 is 64. And 3 times 3 is 9, times 3 again is 27. And with the calculator, we can calculate this. It's going to be 2.37. See, if you double the 27, you'd have 54. So it's a little bit more than double. And let's now go to one more case where we have every 3 months, we apply 25% interest. In other words, you get a quarter of our money back every quarter of a year. So that would give us 1 plus 1/4 to the 4th power. So this would be 5/4. 1/4 is 5/4 to the 4th power. And that would be 5 times 5 times 5 times 5, taken as a factor 4 times, and 4 times 4 times 4 times 4. Now 5 times 5 is 25. So we want 25 times 25. And 4 times 4 is 16. And we want to have 16 times 16. This is 625. This is 256. And when we divide this, we could use our calculator here, 2.44. And again, more than $2, more than $2.37. In other words, this kind of interest, this is called compounded interest. So we apply the interest during fractions of the year and apply a fraction of the interest. And look at that, we get interest on interest. So the question is, what would happen if we had every, say, 1/n of a year, and we did it n times? That's the general formula for what we've been doing. If n is equal to 2, then we have n is 2, see? And then if we had the case where every 1/3 of a year, we'd have a 3, and then we'd have a 3. And then here we have, say, 1/4 of a year, a 4, and we do it 4 times. And I want to look at the limit as n goes to infinity. So by looking at that, then 1/n is going to go to 0. So this is like having your interest compounded moment by moment to do this. Now, if we make a graph, say if we make a graph of this, and we were to have, say, 0 here, and this is going to be 5, we'll go 5 here. This is going to be our n. This is going to be what our n is. And then we look at, say, 10, and say 15, 20, right? Then we have done the case where n is equal to 1. Well, actually, if n is equal to 0, you would have then no gain in your money. So actually, this ground line is 1. And then if you have, let's say, 1 time you apply the interest, like every year, then you would have $2. See, so that would be, say, up here you'd have a 2. The graph would jump up to there. So that's pretty impressive. See, and then if you go on and on, you'll see it doesn't increase as much. When we had, say, 4, which is here, it was $2.44. So that would be like 250 be, to say, half of that up there. So that's really not, see, it's doing something like this. And if you go out to infinity, it's going to approach a certain level. And that is $2.72. So this is not the scale. Here it is in our book where I had the spreadsheet do it for me. And you can see that it's approaching 2.7 something. what this is, it would be 2.71828, and this would keep going. This would keep going. And this is by definition E, and that's the special base. Now what about e to the x? Well, we know that e to the x would be, I would first write down e, which is the limit as n goes to infinity of 1 plus 1 over n to the nth power, and I would take that to the x power. So when we do that, we get n times x for the power. Like for example, if you had taken, say, 2 cubed, and you were to go squaring that, you'd have 2 cubed times 2 cubed, and the exponents would add. So you would have here 2 to the 6th power. So you can think of that as multiplying the 3 times the 2. And then you get the 6. So we multiply x times the n. And we would have here the limit as n goes to infinity of 1 plus 1 over n times nx. Now what I'm going to do is a trick. I'm going to let m equal n times x. Now when n goes to infinity, m is going to go to infinity also. So I'm going to write the e to the x as the limit as n goes to infinity of 1 plus 1 over n, but what is 1 over n? All right, let's see if we can replace that. Well, n is equal to m over x, and 1 over n would be then x over m. So I'm going to do that for the 1 over n part that's here. I'm going to replace it with x over m, and then for the nx, m, and we need to make this an m. Since I don't have any n's in here, we would like to replace that limit of n going to infinity with m going to infinity. So let's go ahead and do the relabeling. So this is the limit as n goes to infinity of 1 plus x over n to the nth power. So I can use this formula here as the general formula for e to the x. I have a function now. So if I let x equal to 1, so I have e to the first power, I would have the limit as n goes to infinity of 1 plus 1 over n to the nth power, and that would have to be e, and that's what I have up above here, the definition of v. So everything works out nice. I have my function. And we could let, say, x equal to 1 would mean your interest rate, you're getting 1 full amount back moment by moment, adjusted for moment by moment. So you're getting 1 full amount back, 100% back, but when you do moment by moment, you have to divide by n. This is going to go to infinity, and then you apply it n times. If you were to let x equal 1/2, that would be 50% interest, since when x is 1, that was 100% interest. And then when x is 0.5 or half is 50%. But I'm not interested in that. I already have the function and I want to take the derivative of it. But before we do that, let's point out some interesting things about this number. This number e that we've already figured out to some decimal places. Now you can go more and more, and you could use powerful computers to get you more digits. 1-8, say 2-8 like this, and go dot dot dot. You will find that these digits never repeat. So since there's no regularly repeating pattern, when I say they don't repeat, I mean a pattern doesn't repeat, like 0.33333333, or point say 151515. They don't repeat. So when that happens, we say we have an irrational number. So let's go ahead and note that. Irrational, the number is irrational. But now when the number cannot be expressed as a solution to an integer polynomial, for example, let me give you one, say like x squared is equal to 2, then x is equal to the square root of 2. This likewise has no repeating pattern that goes over and over again. See, a repeating pattern would be, for example, if you had 0.3333, that's going to be 1/3. When you don't have a repeating pattern like this, then you have an irrational number, but it can be a solution with an integer polynomial. Now, a transcendental number is one that cannot be given as a solution to a polynomial with integers. An example of a transcendental number that we're familiar with is pi. You can't get pi by a solution of some algebraic equation where you have integers and powers. And e is another example of a transcendental number. So these are very special numbers. So irrational number that also cannot be expressed in terms of a integer polynomial. And you can't cheat by saying something like x minus pi is equal to 0, because that's not an integer polynomial. For integer polynomial, you have to have like a constant plus some constant times x plus another constant times x squared, and etc. So now we want to find the derivative of this. So I want the derivative with respect to x of e to the x power. So I want the derivative with respect to x, and I put in my definition for e to the x, the limit as n goes to infinity of 1 plus x over n to the nth power. Now I'm going to use the chain rule. So I'm going to look at this as being some u, all right? So we're going to look at taking the derivative with respect to u. So if you have u to the n, the derivatives, you just pull the n down, and you have u, and then you have the n minus 1. So I'm going to pull this n down and do that. So here we have the limit as n goes to infinity. We're going to pull the n down and then have 1 plus x over n to the n minus 1. But now I have to take the derivative of u with respect to x, which is inside here. It's going to be the derivative of a constant is 0. And this x over n, the derivative with respect to x is going to be 1 over n. So that's what I'll have. Now I'm going to notice that this n and this 1 over n will cancel. So for the derivative of e to the x, I'll have the limit as n goes to infinity of 1 plus x over n to the n minus 1. But now, when n goes to infinity, n minus 1 goes to infinity. All right? So therefore, this is the same as the limit as n goes to infinity of 1 plus x over n to the nth power. But wait a minute. It's the same thing. So in other words, the derivative of e to the x is e to the x. Wonderful observation. And that's for that special base, e. And that special base, e, means when you compound interest moment by moment, you get this kind of a function, this e to the x. For example, if x is 1, that's 100% interest, then you would have e. Very, very special. I would like to do one last thing now. We did show that d dx of e to the x is equal to e to the x. And e to the x is the limit as n goes to infinity of 1 plus x over n to the n. Now, I like to work this out and show you explicitly from a power series that this derivative is going to be the same. So remember back in an earlier class, we looked at the binomial to the nth power, and we had a formula. A to the n, b to the 0th power, and then we had here n over 1. I started at the end, and I start at the beginning, and just have one factor in each case for the first term. This is the 0th term. And then this is a to the n minus 1, and this is b to the 1. Then for the, what I call the second term, you would have n counting backwards, just 2 factors. Then you would count upward from the beginning, 1, 2. Then you would have a to the n minus 2, b squared. Now let's do one more. For the third, you'd have n minus 1, n minus 2. You would have 3 things. That's counting backwards, and then you would count forward, 1, 2, 3, and then have a to the n minus 3 and b cubed. Now, in this case, the a is going to be 1, so these are going to be all 1s. So I can apply this with the 1 plus x over n, like this. And that's going to be 1, because a is 1. And then here to the 0th power, so this, a is 1, and this is the b, x over n. But to the 0th power, that's going to be 1, so I'm just going to have a 1 there. Then I'm going to have n over 1, and I'm going to have, 1 to any power is going to be 1, and I'll just have 1 power of the b, which is x over n. Then for this next term, I'll have n minus 1, and then 1 times 2. A is 1, so any power is 1, so I don't need to worry about that. I'll just have x over n squared. And I'll do one more, n minus 1, n minus 2. And then I count from the front up, 1, 2, 3, 3 terms for the third term. Well, I'll say 3 factors. And then x over n cubed. All right. Now we're going to want n to go to infinity, and that's not going to affect 1. So in other words, you're going to still have a 1 here, and this n is going to cancel that n. So you're going to have x. Now what about this one? Let's look at this one. Well, I'm going to work this out. This is n times n minus 1 is going to be n squared minus n over 2. And this will be x over n squared. So let's look at that term. And here, you're going to have a 1/2. You're going to have n squared over n squared. And then you're going to have your x squared will be there. And then for the next term, you'll have minus 1/2 n over n squared will be 1 over n, like this. And this is this is x squared. So let's check it. 1/2 n squared over n squared. It's going to cancel. And then 1/2 minus n over the n squared is going to be 1 over n. What's going to happen here, see, this part is going to give you a 1, and this is going to go to 0 as n goes to infinity. So what this one's going to become is simply 1/2 x squared. Now, let's do the third one. Let's do one more here. So this is going to be n times n minus 1 times n minus 2 over, I'm going to write down 3 factorial here. And we could actually call that 2 factorial. And this is x cubed over n cubed. So if we work out this, we would have n times n minus 1, say n squared minus n, and then an n minus 2 over 3 factorial, and then x cubed over n cubed. So this is going to be n squared times n. That's going to be n cubed. And then n squared times the minus 2 will be minus 2n squared. Then the minus n times the n is going to be minus n squared. And then minus n times minus 2 will be plus 2n. And this is going to be over 3 factorial and this n cubed. Now the n cubed will cancel this n cubed, but look what happens over here. When you take n squared over n cubed, you'll have an n left over in the denominator for that second piece. The third piece will have n squared over n cubed. That'll leave a 1 over n, and this n over n cubed will leave a 1 over n squared. So that means when you take n to infinity, the only one that's going to survive is the first one, where they cancel. Since there'll be no n, there'll just be this x cubed over here over 3 factorial. The other terms will vanish because there'll be at least one n in the denominator for each of these 3 pieces. So if we summarize what we have so far for e to the x, we would have the 1 plus x. Then we would have plus 2 factorial, 1 over 2 factorial times x squared. And then the third term would be x cubed over 3 factorial. I think you could see the pattern here. You would get x to the 4th over 4 factorial for the next one. Now, if I take the derivative term by term, with respect to x, the derivative of 1, that's a constant, is going to be 0. And then the derivative of x is going to be 1. And over here, when I take the derivative, I'll pull the 2 down, and I'll have the x to the first power over 2 factorial is 2. Then here I'll pull the 3 down and have x squared over 3 factorial, 3 times 2 times 1. And then over here I'll bring the 4 down, I'll have x cubed. You drop 1 power when you take the derivative. And that's going to be here 4 times 3 times 2 times 1, because that's 4 factorial. Now look what happens here. You get 1 plus x plus the 3 cancels. You have x squared over 2 factorial. Here the 4 cancels. You have x cubed over 3 factorial. And this is the same. In other words, the derivative is equal to the same power series. We show that with the power series, term-by-term differentiation, the derivative of e to the x gets you e to the x. And that's a real nice conclusion to see it a different way. It's always nice in math and physics and in general if you can do things more than one way. So this is our summary. In this section, we wanted to take the derivative of e to the x, and we've looked at it from a couple different points of view.